Greetings. Welcome to Environmental Systems Engineering 408, Contaminant Hydrology. Um, my apologies for not being with you today. If it's any consolation to you, I should be a few hundred miles north of Pyongyang, and I'm pretty sure that wherever I am, the weather's going to be a little cooler than where you are right now. So what I want to do today, so my apologies for not being with you, but what I want to do today was do three things. I wanted to give an introduction for the class in terms of an overview of what we'll attempt to do. I wanted to set up the things that I'd like you to do in lieu of class on the first Tuesday and Thursday in preparing for our second week when I'll be back. And then I wanted to talk about the things that we'll do in the second week in terms of what I'd like to attempt with flipping the classroom, so-called flipping the classroom, to do things a little differently in this class than we've done in the past. So those are the three things that I wanted to cover today. So if you're listening to this, you already have found yourself to the right YouTube link. All the materials for this class are on Angel, and so you can grab them right there. And so what I'll do first is give just a brief introduction to the class and talk about the things that we'll do. We will meet most weeks, Tuesdays and Thursdays in the afternoon in Hammond. The class recordings from previous years will be available on YouTube. And my intention, I think, this time is to have much more interactive class time sessions. So I'm going to flip the classroom. And so what that means is I'm going to ask you to review the materials we've recorded in the past to bring you up to speed on the different topics. And then when you come to class on the Tuesdays and Thursdays, we'll work through either the homework examples or some extension of the homework examples, which you'll then submit. So it should be an easy deal, but you'll have to participate. So I guess the good thing about it should hopefully be that there'll be more interaction. And maybe the bad thing about it for you is that you need to turn up. There is an attendance policy. So you can't do this without this component of interaction. So those are the pluses and minuses of doing this. All the materials for the class are online. And if you look at the Angel website, there's a link to a web page which has the same materials that we will talk about. It has the class notes. Probably the easiest way to get the class notes are to download them from this large 70 megabyte file, which is available online and will take some time to download, but it's a compilation of all the materials that we'll deal with in class. And so that's one convenient way for you to be able to get access to that. So you've certainly seen those kinds of things before if you've taken 303, which probably most of you will have done. And the materials in terms of videos will be available on YouTube. And as I say, if you're looking at this right now, you've already found your way there. There is a textbook for the class. It's not required. If you are making this area of endeavor, contaminant hydrogeology, your profession, you may consider buying it. I think it's useful. We don't do any assignments from the textbook, but it gives you background information to the behavior or the items that we'll talk about in class. And so it might be useful for you to get it, but it's up to you, of course, whether you want to do that or not. I didn't introduce myself. I'm Derek Ellsworth. You may have seen me before. The TA for the class is Chuan Gan. His office is right next door to mine in Hosler, and Chuan will take care of your needs for questions you might have related to the homework assignments. But my hope is that we can actually do a decent job, maybe of explaining and going into a bit more depth in the homework during the class time periods and doing some other things. In terms of prerequisites, GSci 452, hydrology is a prerequisite for the class. You can probably get by without it, but it's a pretty useful component and should be taken before. I guess it would be before. I don't think it's offered this semester, so it wouldn't be concurrently. The grading for the class, it's a lot more relaxed than other classes you might have had with me in terms of kind of interaction. It's a small class, and assignments make up 40% of the grade. As I say, we'll try and flip those during the class periods and see how that works at least. There is one midterm exam. The date of the midterm exam is tentatively set for the Tuesday before spring break in class on the 4th of March. So we'll stick with that for now, and that's worth 20%. Typically 3 questions. The old exams are present, I think, online. If you go to the class webpage, which is the link that we looked at earlier on, which is this, then the previous exams should be there for 2012. I guess the 2013 ones aren't on there yet, but you can get the exams for the previous years to work through those if you so wish. And so typically the exams are 3 questions. First question is a definitions question, and the other 2 questions are typically calculation questions based on what we have learned in the class. So relatively straightforward in terms of that. There will be 2 other deliverables. One is a remediation presentation, so it'll break you into groups of 6, or 6 groups rather, and in those groups you will investigate around some rubric and make a presentation on one of 6 different remediation methods that can be applied in aquifers to clean up typically dense or light non-aqueous liquids. And you'll present that in class in the last few weeks of the course. And also a project which deals with remediating a site where you're given some data that describe the stratigraphy at the site, the form of contamination at the site, and allow you to develop a method to be able to effectively remediate it and cost out the expense of doing that. So the last 2 projects are kind of related to each other in that typically you need to know about the remediation methods to be able to understand what you might apply. And for the 6 different groups, the group projects are related to trying to use that remediation method that you will have investigated and will have presented to be able to remediate your site. So those are the 4 main deliverables. Assignments due most Thursdays, a midterm exam just before spring break, and a remediation presentation and a class project to look at remediation solution for a given site. So it's a pretty straightforward class in terms of the material we'll deal with. In terms of the topics that we'll cover, they're given in outline here. Perhaps I don't need to go through it, but we'll spend the first period today giving an introduction of what we'll talk about, and also talk about some projects and some key places where contaminant hydrogeology is in the news related to Marcellus Shale, destroying groundwater, for instance, nuclear waste disposal, and other contemporary issues which are of some importance. So we'll do that today. And then on the next time we meet, which will be another virtual meeting, we'll start off by talking about physical hydrology and trying to understand single phase flow within systems, which of course is something that you should have dealt with in some detail within groundwater hydrology, GSI 452, if you've taken that as a prerequisite. But we'll talk about, starting off with single phase flow, we'll talk about dual phase or multi-phase flow when you get other invading species. And so in the grand scheme of things, we'll talk about how you get contaminants into the ground, such as gasoline or denser than water non-aqueous liquids, how they propagate in the subsurface and come to rest somewhere. Once they've come to rest, we'll talk about how they can be remobilized from that location and carried down gradient to a compliance point by dissolution in water and movement by either diffusion, dispersive diffusion, or by advection. We'll talk about systems where, in addition to being carried down gradient, there is also a reaction that occurs with the aquifer substrate that it goes through, and so the levels of contaminant that you ultimately see downstream are reduced over the amounts that they would be if they didn't react or interact or sorb in the aquifers that they are passing through. We'll talk about mechanisms by which some of these components, which are volatile, can off-gas and can be used to advantage as a remediation method, but can also happen as a natural consequence of being disposal in the vadose zone, where some of the mass will be lost just due to volatilization, and how we quantify that. We will apply some mathematical models to look at flow and transport in porous media, to be able to look at dimensioning remediation methods, to say how long it will take to remediate sites, and what will happen if we don't remediate sites in terms of where the contaminants may end up and what the loading levels might be. So we'll develop a rudimentary understanding of mathematical models to do that. We'll talk about methods by which we then evaluate aquifers to be able to supply the fundamental data that we need to answer all of these previous 5 or so questions, in terms of how quickly can the stuff get into the ground, how quickly can it be transported from a source location, will it be attenuated to some significant degree, and if so, by how much, will some of it be lost by vapor transport. So the parameters that we need to be able to use in mathematical models to be able to describe those behaviors, we can only get through methods of characterizing aquifers. And we'll talk about the different methods of site investigation, drilling and sampling, that allow us to say something about the characteristics of the aquifers, which we need to be able to say something quantitative about how quickly these fluids can actually travel in the subsurface. And then you'll be on deck to then talk about remediation in these 6 or so different methods that can be applied to remediate sites. So that's kind of where we're going with this. There really is only one textbook for this, which is Fedder's Contaminant Hydrology book. You may use Fedder's hydrogeology book for 452, but this is a different book, and so you might want to look at that and consider making that purchase. There are other background books on reserve in the library. The most notable when we talk about multiple phase flow is Baer's Dynamics of Fluids in Porous Media. I'm not really sure you necessarily need to go back to any of these books, but they're certainly there if you want to be able to delve more deeply into the topic. In terms of academic conduct, you're certainly encouraged in this class to work together, no doubt about that, and certainly some of the work is group work, but you're requested to submit your own work, certainly for the assignments, but group work for the things which are group work also. There will be peer reviews, as we've used in the past, so that your colleagues in your groups can comment on how much of your weight you actually carried in the work. Because we're going to flip the classroom, and I'm kind of curious to see how, if we can get a little more interaction in this class rather than me talking and people listening. So I think we'd like to flip the classroom and do things that way. So attendance is expected, and basically you need to turn up. And if you don't turn up, we'll track you down and see where you are. The deliverables are assignments. They are a midterm exam and these 2 other projects. Evaluation of remediation methods, and also a design project for a particular site which happens to be in Virginia. The scaling, or the scheduling rather, of the things that we'll do in this class are given here in the outline. These are the Tuesday classes, these are the Thursday classes. It may change, but basically the first part will talk about flow of multiphase fluids up to here for the rest of this month. We'll talk about transport and remobilization of those fluids, including the vadose zone. We'll talk about aqueous transport, both in terms of conservative species and in terms of non-conservative species where it reacts with the aquifer. We'll talk about behavior in the vadose zone. I guess I didn't relabel this, I'll change that. This will be the midterm exam, so this will just get offset by 1 week. So anyway, you have a rough idea of the kinds of things that we will do. So that's kind of an overview of the class. The second thing I wanted to mention was that since I'm somewhere north of Pyongyang, is that what I'd like you to do in view of this Tuesday and this Thursday are to look at the first 2 YouTube videos. The first one will directly follow on to this discussion here, as the continuation of this file. And the second one is to look at the first installment, if you like, of physical hydrology and the transport of non-aqueous fluids in the subsurface. So please do have a look at those before the second Tuesday of the month, which will be the 21st, when we'll meet in class and we'll talk about what you've understood from those materials and also make a start on the first assignment in class. So you might want to review the first assignment, which is online on my website. And so the third thing is that you should come prepared to do those things that we're talking about. So please do look at these videos. Please do understand them. Please do come prepared to discuss them when we're in the classroom. And please also think how they apply to being able to solve the components of the first assignment, which we'll go through in class. So that's our plan. Okay? I will leave it at that, and this will continue on from this in terms of an introduction to physical hydrology. Okay? Thanks very much.
So on the website, on Angel rather, are 301 pages of scintillating notes that you'll want to download and put on your computer or use in some way. We'll use them in this class. It's kind of interesting, since I started using this pad and computer last semester, because it's always tough to actually get a room that actually has the things that you need. The things you need are something to project something on and something to write on that you don't have to raise the screen up and down all the time. So I guess I got my wish, although I don't necessarily need it now because I tend to do this and record it. But the notes are present here. They're divided up into these individual chapters. You'll see a blank page somewhere. So they're basically subdivided so you can see what's going on. And I will use those. I mean, it might be interesting also, everyone talks about flipping the classroom, right? So you do this, you record it, you allow people to look at that material in their own time, and then you do something else in the classroom, maybe like going through homework examples or derivatives of homework examples or real-world problems or doing something like that. So I'm not sure what is actually going to work out, but we'll see. We'll see as we go down the road. So, but the basic resources for this class are mainly this reader. The other thing that is in the tail end of this, if you go down to, is a section on remediation. And of course, this is the stuff that I've usually talked about in class, but I'm going to get you to do this because I'm bored of talking about it in class. And I think it'd be a useful thing for you to do. And so this material is actually divided up into these segments that talk about these 6 different classes of methods. I'm not sure how this is going to class. If we're a class of 24 or so, then I guess that would be 6 groups of 4, which is actually probably about perfect for this. So you can let me know how you want to do this. I'm happy to do the kind of random automatic team generator thing work on Angel if you want. Sometimes that's the easiest way to do it when people don't know each other in a class, but I imagine there's a cohort in here of people who perhaps want to work together. And so I'm okay if people want to kind of divide into groups of 4s, and the people who aren't kind of in that community, we can work up as a team. So maybe we can do something with that. Maybe I should let Taha figure that one out for you. So, were you paying attention, Taha? You were looking at the notes. So yeah, so we can do it either way. I don't mind. I'm fine. In 303, we have everyone work in groups that are prescribed, with the suggestion that, well, when you work in a company, you don't get to choose who your colleagues are. You have to work with them, and you have to solve problems. If you don't solve problems, you get fired. And so there's no other way to interpret that. But in this class, I'm more inclined. In the past, I think we've let people choose their groups. And then people who don't have some communal connection, we certainly have individuals from other programs here, we can team up in some other way as well. So you might want to think about what group of 4 some of you might want to work in, then we'll make the other arrangements as we go down. We don't have to do that immediately, but think about that if you're in that boat. And I sidetracked myself, but if you look at each of these topics is divided up in exactly the same subheadings that the rubric is for the presentation. And so I'm not suggesting that you use these notes verbatim. These notes in themselves come from a book by Grubb and Sitar, which is one of the books on the back page of your syllabus. Now a bit out of date. It's 1994. Certainly things have moved on, but it gives you some, at least somewhere to anchor it. I used to leave it in the library until someone didn't return it one day, and I never replenished it. So it isn't in the library, but I'm sure it might be on microfiche or something there. But so you can get access to that. But anyway, the presentation of that material in that report and in this stuff on the screen is follows exactly that rubric. So there's hopefully something of utility, at least, in these 301 pages, and hopefully you may be even able to see them. What else? Okay. So, any questions yet? No. All right. No texting in class. No texting in class. So don't no. Actually, it's maybe counterproductive. But if you're going to spend, fine, send a text if you need to send a text. But if you're going to spend the whole time texting, don't come to class. It's pointless, right? So I never understood it. So anyway, am I being too rational? Huh. No, she says. Yeah. All right, so I won't make you go around and introduce yourselves to the class individually. What I've done is I've always given this kind of, today is just an introductory period to be able to talk in general about contaminant hydrology and why it might be important. So there's nothing really to note from here that you need to write down. So you could text today, but you probably shouldn't. And I'll just talk about a few projects that have kind of that are local that make some sense. So I made this this picture here. So it may seem like a random picture, of course, but this was, what day is today? Tuesday. This was the winter solstice, December the 21st, so it's 3 weeks ago. This guy here is a guy who's Ed Miser. There's a hydrogeologist, this is my house, this is me, in my alternative wear, for a summer solstice party on a Friday night, on the Friday before Christmas, if we're allowed to say Christmas these days. And so Ed Miser is someone I worked with, I think it was 1994, so what is that? That's a long time ago, right? 20-some years ago. Yeah, almost 20 years. Yeah, almost 20 years ago. And the project was in Roaring Spring. And just talking in generality about it. So Roaring Spring is a town that sits on a spring. The spring is fed by a strange geological structure. The geological structure is a fold where rocks have been folded over the top. And so if you imagine things are flat lying at some time, they get bent like this to look exactly like what's on the screen. And as a result, you get some big, if it was really thick, if you imagine taking a telephone directory and bending it across like this, the top of the directory is in tension, the bottom's in compression. And if it's in tension, you develop these kind of tension fractures that break open. And if those fractures are open, they allow water to infiltrate into this and to travel down through this. Well, that's not quite the system that they have. But what they have in Roaring Spring is it's a two-industry town. There is Appleton Paper Company, which I think uses 500,000 or 5 million, I guess it's 500,000 gallons a day in pulp production for one of those stinky paper mills. And there's Roaring Spring bottled water, which is not quite as illustrious as the Jopa bottled water, but it's the same idea. You get something for free, you bottle it, and you sell it for something that costs more than gasoline if you look at the price per unit volume of it, and which is a relatively low volume user. And the other third company, which isn't so related to the water usage of the spring, is New Enterprise Stone and Lime. And New Enterprise Stone and Lime is a limestone quarry, and these are limestone beds that are bent over. And originally the ground surface was like this, and slowly over time they've made a quarry out of it that has progressively gone deeper and deeper and deeper. And the hydrogeology of this site is that this fold, which is present, runs along the high wall of the quarry. So if you look at this kind of from a perspective view, this is this fold that's been bent like this. This is the hinge of the fold, which is this red thing that comes along here, which is this broken area. And the quarry, if you like, is where my fingers are here. And all the groundwater flow comes from rainfall that lands here and gets pushed over in the beds to the east side, let's say, until it hits this fractured zone, which is very permeable. And all of a sudden, the water that's happily flowing across here gets captured by this really permeable stuff, and it gets kicked right the way down to this spring, which is where it has a topographic exit, and it flows out of the side of the mountain. And Appleton use it for their paper mill, and Roaring Spring Bottling use it for their water. And so that's fine. So these are the big industries in town, especially the 800-pound gorilla, which is Appleton Paper Company. And New Enterprise wanted to change this. Wanted to change this by digging progressively deeper and deeper. And so the worry is that basically this is a groundwater dam. Bless you. These are vertical beds that have very low permeability across them, so that any water that was flowing in this direction was actually just like a surface dam. It wells up behind it. It wells up behind it, and the only way that it can flow out is by flowing a long strike along the edge of this fold into the down gradient, into the exit point where it goes into this, where this crops outside the ground surface. And so the worry was, if you start removing this material in these benches, all of a sudden you allow this to physically move in, the rock to physically move in, you break open some fractures here, and now no longer is this a groundwater dam. And so the reason for showing Ed Miser there was because when we were chatting on Friday night, he said that 18 years on, apparently the predictions that we had that if they did this in some kind of staged approach, and we did some calculations to see how the permeabilities would change here, all of our predictions came to pass, and they did exactly what they wanted to do. So I think that was kind of good news, that we're not at least getting sued for something, and the predictions, it's always nice to know that your predictions come true. And so groundwater as a potable resource is an incredibly important and quite emotive topic anywhere in the world, and certainly in Pennsylvania as well. So just an aside. So it's something that we did maybe, I think it was, maybe it's 92, so it's 20 years ago or so. And this is kind of a geology map of the same thing. This is the quarry right here. If you know anything about geology, these are the folds which are dipping into the ground, and the ground cuts across them. And the Roaring Spring is somewhere down. It's down here. I don't know exactly where it is. So it's along here somewhere. It flows down here into the town and then comes out from there. So I'm not going to worry about that. I'm not going to talk much about this. This is Tajas from India. This is a big lignite mine in eastern India near what was Madras. I guess we should change that, right? One N? Yeah, two N's. Okay, Chennai. And this is a mine that is relatively close to the Bay of Bengal, this is the Bay of Bengal here, and it's happily sitting here. And of course, as you mine this material out, the water table is relatively high. The coal that sits underneath the water table has to be removed by physically digging down into the subsurface and intersecting the coal that's there. The coal is underlain. I guess I actually have a better picture. This is the Bay of Bengal. This is this lignite bed which sits here. This is the mine, not this exaggerated horizontal scale. This is the mine that's gone into it. And it's underlain by all of these clay beds. And the clay beds, what they do is they stop the fluid from rising up through here. And so any fluid that sits here with the water table has some pressure attached to it. So it sits under here as being overpressured. And as soon as you cut through this, basically the water breaks into here, and you need scuba gear to be able to remove it. And so one way to be able to not have your trucks using scuba gear and your miners using scuba gear is to put well bores down and you pump it. You pump it out and you depress the water pressures that are underneath here. You use the water that comes in from this, and actually as you drive from Chennai 100 kilometers to this mine, you go from really kind of semi-arid countryside to really verdant countryside, because all the water that's being taken out of this is fresh water, is being used to irrigate the surrounding farmland. So that's great. Everything's good, right? You're getting coal out, you're burning it, so you're creating electricity for the country, you're using water as a resource to irrigate the fields, that's great. But the negative is that because it's so close to the Bay of Bengal, and this is actually salt water, this is salt water, is that as you physically suck water in from here, then you move this front progressively further and further into here. And it's the same problem that they have in Florida as well. You pump groundwater out of Florida, relatively narrow state. As you pump groundwater, something has to come in to replace it. It could either come in as water from the surface, typically not the case. It comes in from the sea, from the side. So if you don't balance the rates at which you're removing water out of the system with the replenishment from rainwater in this particular case, then ultimately what you're pumping is no longer fresh water, it's actually saline water. And that's not very useful if you want to grow crops. So incredibly important to understand that. It is a contaminant hydrology problem because this is salt water, not fresh water. It's a contaminant to the existing aquifer that existed previously. So another example of a practical, pragmatic case. Yeah, let's talk about this now as well. I'll talk about it in a slightly different form in a second as well. So certainly, no, let's come back to this. So what else is it? Yeah, no, let's do it now. Indecision kills. So, I mean, one of the big problems in terms of energy supply is what you do in the high carbon environments that we live in if you want to physically get rid of or reduce carbon emissions. So if you want to reduce carbon emissions, probably 50% of the electricity we get comes from coal generation. It's changing slightly with kind of Marcellus gas type things in that some of the electricity production now is by burning gas rather than coal. But the ways to reduce your carbon footprint, if you like, would be to replace coal with gas because there's lower carbon per BTU as you burn it. To take the CO2 that comes out of the coal burning plants and to pump it underground as carbon capture and storage, which is a multi-phase flow problem, not very completely identical to the things that we'll talk about in this class. You could generate your power from other methods, or you could use nukes. You could use nuclear power. We probably get 10% of our power from nukes in this country. They probably get 50% in France. The Japanese used to get a third, but since the Tohoku earthquake, I was in there about March a year ago, and their very last of their 53 reactors closed down immediately after I left, which is a third of their power, and they have brownouts. So, but one of the big issues with nuclear power is, for sure, the Fukushima issue of having a tsunami hit you, which probably isn't very likely in many places, and certainly we'll be wiser now and not put generators on the ground floor versus high up where they can actually keep running as they get inundated to be able to keep water flowing through the reactor core so it doesn't shut down and you have core meltdowns. But the other activity in the kind of nuclear fuel cycle is what to do with the waste. And so every industrialized country, including the US, who has nuclear power, has a program to be able to dispose of radioactive waste. Almost all of those disposal programs are to put it underground. The repository for the US was Yucca Mountain before the Obama administration stopped it shortly after they hit their election in January 2009. So Yucca Mountain, there is no home for it in the US right now, but all the other industrialized countries in the West have plans to put it underground in different, typically in a repository that looks something like this. It would typically maybe be 300 meters deep, 1,000 feet deep. It would be basically a mine that you'd mine out all these tunnels, and within these tunnels you would work on the idea of redundant barriers. So the same way I always like to say that a plane has two wings, you always like to have an extra wing in case one drops off when you're flying. You'd like to have multiple barriers to be able to, yes, no, it's a joke. You'd like to have multiple barriers, so if one barrier is breached, you can actually take care of the fugitive emissions. So typically the idea is that you have a cask, you vitrify the waste, so you put it in a glassed form so that any water that goes through it isn't able to leach out the radionuclides. You put this waste form inside a big cask, which is, the size of this is typically for the Yucca Mountain project would basically be probably 2 meters across, and the size of a kind of a railroad car that you see going through Pennsylvania and elsewhere. You drive these casks underground into a bunch of tunnels. Once these casks are underground in the tunnels, you backfill around them to be able to fill up all the space, so that if the roof collapses, it doesn't rupture these casks and therefore spill the contents. And in addition to that, you make sure that when you put these tunnels in something, you make sure you put them in some really low permeability rock, so that the flow rates of water through that are so low that even if it does rupture, and of course the designs for these are to last about 1 million years, the EPA design requirements for the design of a repository is for 10 to the 6 years, so even if they rupture, the water is flowing through so slowly that the material that gets leached out is in such a slow rate that the dosage to anyone who consumes this down gradient is tiny. And so the idea of multiple barriers is to be able to encapsulate the waste and keep it far from us. So we won't talk about this really in this class. We'll talk about a very different method of a very different focus. But the principles that we'll talk about in this class in terms of unsaturated flow are exactly the same as dealing with fugitive emissions from something like Yucca Mountain. The main thing that we'll talk about, however, though, is on non-aqueous phase liquids. And the reason that we do that is because it's kind of the hardest problem that we could choose. And so it's hard because you have to deal with the flow system first. You have to figure out exactly how fluids will move in the subsurface to get to some equilibrium location. Once they sit there, you have to figure out how quickly they will dissolve into groundwater and then become mobilized in the groundwater. And then if you have them dissolved in the groundwater, you have to figure out how quickly they'll travel to some compliance point, which is where you're taking them out of the ground and drinking them out of your drinking well at your house or in your municipality. And so if you understand this problem, you basically should be able to solve most of the problems, the other problems that we'll talk about, which are related, but which we typically won't spend much time on. I'm just trying to give you some perspective of the range of problems. And so the processes that we'll talk about will be things like spilling gasoline into the subsurface, where if you have an underground storage tank, or if you happen to spill it on a garage forecourt, for instance, it will soak into the ground and it will go into the subsurface. But because gasoline, as you know, is lighter than, less dense than water, rather than keeping on going once it hits the water table, it will actually be buoyed by the fact that you have water. It will slightly depress the water table, but it will sit on top of it in a lens which is some shape. So this would be the gasoline, which would sit here. And on the pathway that it's taken, it will leave a smear of gasoline in the pore space, which is partly filled with water, but mainly filled with air, and now is filled with gasoline as well. And it will push down the water table because now this free product gasoline, which you could just suck out with a straw and put it in your car and drive down the road with it as well, because it's in that same form, will also slowly dissolve into the groundwater which is flowing underneath it, and it will get carried downstream as some kind of plume. And so over time this plume will be here, and then it will go further and further down. And so that all of a sudden, if you have a well which accesses this at some location, and you pull the fluid out of there, then once this plume has reached you, then no longer you're drinking pure water, but you're drinking pure water with maybe a few tens or hundreds or thousands of parts per million of benzene or toluene or xylene or xylene, which are the components of this. And so that's one form of this. And we'll also look at, for instance, if you look at spills of compounds which instead of being lighter than water, like gasoline or diesel fuel, are actually denser than water. There's no reason why they would actually sit on top of the water table, but they'd scoot all the way down through it, and the only reason that they would stop is because they hit some kind of barrier. And it's not necessarily a permeability barrier, but it's a capillary barrier, and we'll talk about that in due course. And so here you'll have exactly the same case. You'll have this free product that sits here as a lens, just as we did above here. Water, groundwater will be flowing past it. It'll flow through this kind of chimney, which is partially saturated here, so it'll be in the pore space, it will be air, there'll be a little bit of water, and there'll be some TCE or other solvents in here as a remnant from here. And as you go across the groundwater table, then this is purely saturated, but it'll be saturated with water, but in this upper region it will also have a little bit of dissolved solvent in it as well, or free product solvent, and free product solvent will ultimately dissolve from here and get carried downstream. And so as the water goes through here, you'll get exactly the same effect, that you'll end up creating a plume which at early time and at progressively later times will move downstream or down gradient. And so if you put a well in here and start taking water out, at some stage this will arrive and it'll end up being a problem. And so the kind of problems that we'll talk about, I won't talk about these, I won't go through every single slide, but the kinds of problems that we'll talk about relate to this. We'll work on a site in southwestern Ontario called Smithville, where some of this has happened for denser than water solvents. TCE has a specific gravity of a specific density of about 1.6, so it's 1.6 times the density of water, and mixed up with other nasty things, and we'll do some calculations to be able to at least implement some of the ideas that we've talked about in this class on remediating a plume which is present there. Okay, I'm not going to talk about that. So the other thing that I was going to talk about is this. So just to give some perspective, so as I say, we'll talk mainly on these problems dealing with non-aqueous phase contamination because they're the most difficult problems to solve, and also because if you end up working in this area, typically most of the work that's done traditionally has been in those areas as well. So you're well prepared if you know this material. But I also wanted to give kind of a perspective since we talked, because I actually don't do very much work in contaminant hydrology, but all the principles are exactly the same. Most of the work that we do is related to fluids in energy. And so I just wanted to give a very quick perspective of some of the contemporary problems which are kind of on the horizon. I don't think they're, I guess they're part of the industrial landscape and consultants must be working on them, but it seems as if it's more specialized right now and not so run-of-the-mill. And so I haven't incorporated so fully into the material for this class. So if you look at these two quotes, so does anyone know who Smalley is? Richard Smalley? There's no reason necessarily why you should. He's a Nobel laureate. He's the guy who founded buckyballs. So the particular form of carbon, which I guess isn't diamonds, isn't graphite, but is formed in these geodesic structures, and was really into a very bright guy who's now dead, died young, but had this statement: we can see how energy is the key to solving all of the rest of the problems from water to population. The basic idea is if you can solve the energy problem, then we don't really have a shortage of water on the planet, we have a shortage of potable water. And so if you have unlimited energy, there's no reason why you couldn't desalinate non-potable water to make it potable water, and then that allows you to feed the 6, 7, 8, 9, 10 billion people that we have on the planet, or feed their thirsts perfectly adequately. And so energy is kind of the root issue for many of the things we deal with. John Holdren, anyone know who he is? He's not the current president. He's the current president's ex-science advisor. And so making the point that energy, economy, and environment. Energy is related to environment through a variety of ways. The most obvious one these days is carbon. Most of energy comes from carbon-intensive conversion processes. And so the carbon goes into the atmosphere, has effects on the climate change, and the climate change means that you might want to do something less carbon intensive in terms of producing energy. And so the feedback in that is, sure, we could stop burning coal right now, but can you afford to do it? Certainly the cheapest of the methods to use. Certainly you're externalizing the costs into the future, but certainly it's the cheapest way of being able to do that. So the variety of different ways of solving the climate problem, if you like, are to try and switch fuel usage from really heavy carbon per BTU or per joule usage like burning coal to less heavy carbon per BTU uses like burning natural gas, for instance, or even very low or zero carbon solutions like using geothermal or nuclear power, and I guess those are the other two that come to mind. And so all of those, although they don't necessarily involve groundwater, all of them involve kind of the precepts of this class. Basically, this class is a class on flow and porous media and transport of fluids in porous and fractured media. And so one of the methods to be able to do it is to use geothermal energy. So instead of looking at these geothermal sites which will exist on plate boundaries, one of the contemporary ideas, which has been around actually for 30 years now, is to use what's called enhanced geothermal systems. So in other words, you drill a hole that costs you $10 million to get down to 5 kilometers. You do it under New York City, so you're right where you're going to use the power. You inject cold water down that hole. You frack it by breaking up this so you actually make a low permeability reservoir into a higher permeability reservoir. You look to see where those fracks are going by looking at the acoustic signals, the seismic signals, and then you drill a second hole down to be able to intersect where those fractures are. So now you basically have a geological heat exchanger. You flow cold water down here, you circulate it across your heat exchanger, which you hope has lots of good surface area, is nice and conductive in terms of being able to get water from the inlet to the recovery well, and you bring it up to the surface. It goes down maybe at 20 degrees centigrade, it comes back maybe at 300 degrees centigrade, and you use it to generate electricity. And you keep on doing that for as long as the reservoir remains hot. It's different from geothermal projects like the geysers in California or Iceland or the Philippines, which sit on plate boundaries, which are very specific locations on the Earth. The west coast of the US, for instance, the Philippines, and the Iceland on the mid-Atlantic ridge. This is something that you hope can apply everywhere just by going deep enough to get hot enough water to be able to use it. And the main limitations, of course, are that it costs a lot of money to get down there. $10 million for a single hole is a lot of money, depending on how long you can use it for. So it's a technology that can be used. But there's a huge supply of heat that's available to do that if you want to use that. So one zero carbon or low carbon solution. Nuclear power is the same deal. The main problems of that we've kind of alluded to already, and that is that the storage of this, which was planned for Yucca Mountain, which is on hold right now, is in geological repositories, and the main issues related to that, well, the demise of Yucca Mountain, it was shut down immediately after the new administration, and depending on who you believe, Harry Reid, who you certainly know of in recent months, as what was he, minority whip, right, or minority lead for the Congress or the Senate? Congress. Anyone know? No? Geez, I shouldn't know that. You should know that. So he's certainly a Democrat. So it's either the Senate or the House. Do you know which?
The Senate is Democrat.
Yeah, not control though. Yeah, each has a majority and a minority leader, right? Yep. So Boehmer is for the House. Yeah, and the Democrat. Yeah, and Harry Reid is the House, is the Senate, which is Democrat. Yeah, that's right. But they also have a minority lead as well, which is who? McConnell is Republican for what? Congress, the House, or the Senate? House. No, it can't because Boehmer. It has to be the Senate. So who's the minority for? Who should be Democrat for the House? No civics lessons?
Is that Nancy Pelosi?
No, she's a senator, right? She was the. Oh, could be, right? Is she a congresswoman? Okay, that's assignment for next time. Jesus, you should be ashamed of yourselves. And so what I was going to say was that the deal was that since before I was diverted, so Harry Reid is the senator for Nevada. Nevada is the state where Yucca Mountain lives, and was in opposition to Yucca Mountain as a repository, a U.S. repository. And so as the story goes, the deal was that this Blue Ribbon Committee that reevaluated whether Yucca Mountain should go ahead as the site was something that was put in place to appease the chair of the Senate while healthcare was about to go through the mix. So you can draw your own conclusions whether there's any truth in that whatsoever. Certainly politics would never work that way. You know that. But basically the things we'll talk about for Yucca Mountain are you put these canisters in. So this is probably a 5-meter diameter drift, 15 foot or so. This is probably 2 or 3 meter diameter railroad car with spent fuel in it. It's pushed in, it's driven into the drift, and then it's backfilled and forgotten. And you hope that when this collapses, as it will do over time, that when you live at Long Street, which is your first assignment, by the way, to look at how sick you'll get when you receive the components coming from Yucca Mountain upstream of you, you hope that you're far enough downstream that you don't receive it. The other mechanism to abate the environmental effects of burning too much carbon or liberating too much carbon is to business as usual. You burn coal, you create electricity. Instead of running cars on gasoline, you drive electric cars, and you charge up the electric cars from the coal-burnt power that you produce in the power plants. Sounds bass-ackward, but of course the reason that you do it with coal is that you can re-inject the carbon that comes out of the stack into the subsurface. And so the repositories for that are not drive-in repositories, but they would typically be things like pulling out oil out of the ground and returning CO2 into depleted oil reservoirs would be one way to do it. You can put it in deep saline aquifers, which are present under our feet as we speak. You know, you go down 10,000 feet or so, 3 kilometers, and you'll certainly find saline aquifers which don't contain potable water. You can put it in coal seams, which will absorb onto the coal. So I guess this is a petroleum reservoir, and this is a saline reservoir. So they go into places that you don't want them to be. And the main requirements for those, of course, are that the cap rocks that you have for these, you want to be really low permeability so that you keep the stuff that's in there, that it doesn't come across here over decades, hundreds of years, thousands of years, because otherwise it just gets back into the atmosphere and you have exactly the same problem you have. And so the mechanisms by which you get CO2, which is a liquid at the pressures you'd pump it into the ground, across these low permeability aquicludes or cap rocks are exactly the same mechanisms by which you'd get dry cleaning fluids from the surface across an aquiclude into an aquifer. No different. Exactly the same physics, much higher pressures and slightly higher temperatures, but other than that, exactly the same physics. And so it's porous media flowing in the subsurface. This is a researchy problem, not really a problem that you'd go and work for a local consulting company or a not local consulting company, but it's still the same physics which is going on. And of course, the big thing have you heard the Marcellus Shale? Excellent, excellent. So if you're from Pennsylvania, you hopefully haven't missed that. And so it's the biggest thing in Pennsylvania since sliced bread. It's amazing. If you drive up in northern Pennsylvania, some of you may be from Pennsylvania. Tex-Mex restaurants. You go and sit in the diner in Wellsboro. You get water trucks going past, 10 a minute it seems. Just completely changed the complexion of the rural environment, but it's great. Employment is great. It's a huge resource. But it's not without its detractors, of course, and it's not without its environmental problems that come with recovering gas from deep shales. And those problems relate in a big way to groundwater. They relate to it because each frac job takes about 5 million gallons of water to pump into the ground to massively fracture the shales that may be at 3-kilometer depths. Once you've fractured it, you bring it back out, and it's got all these components in it, some of which you put in when you put it into the ground, which make it work as a slick water frac, which make it things like biocides that stop it from clogging up the pores and all kinds of things, really nasty things, which in very low proportions, maybe a fraction of a percent of the amount, or fractions of a percent of the amount, but still very nasty things. And once it's come out of the ground, it has all of these radioactive norms, naturally occurring radioactive materials, which were locked in the shales, happy being there for millennia, and all of a sudden you've accessed them in this water, and you bring them back up to the surface. So the water that comes up isn't very nice anymore, and actually can't be reused very easily without treatment for refracking, because it typically has lots of sulfates in it, and so it needs to be treated. So you need a lot of water to be able to do it. You have to get that water from groundwater or surface water typically. Once you use it, it's not so easy to reuse because it has been contaminated in some way. The big worry, of course, is that as you frack this shale at 3 kilometers down or 9,000 feet down, that this stuff that was all nicely locked away by these multiple aquicludes and cap rocks that stop it from communicating with the upper regions are no longer intact, and you have groundwater contamination. And the other issue is that you've driven these wells down here through it, and the worry, is, of course, is that these wells aren't completely keyed into the rock that they go through, and they provide pathways either for the water to go through or methane to escape up through the system as well. So gas production is also a big thing. We won't talk about it in this class, but it's a big environmental issue at the research frontier, and I guess also lots of consultants must be working on groundwater issues related to this. It's a big thing because the volumes are so large. So I think now the revised US estimate is of the order, it used to be like 5,000 trillion cubic feet. I think the most recent one is about 200 trillion cubic feet as of 6 months ago. This slide was made much before that. And the US uses, in terms of natural gas, it uses about 21 trillion cubic feet a year. So it's 10 years, 10 years worth of use just from this one field. If you took all of the energy use that the US uses in 1 year, I think it's something like, in terms of natural gas equivalent, it's about 500 trillion cubic feet a year that we use. No, sorry, that's the worldwide budget. So we use about 25% of the worldwide energy budget with 5% of the population. So we probably use about 125 trillion cubic feet of gas per year as equivalent 125 trillion cubic feet of gas equivalent per year if you satisfied all of the energy uses we have. So gasoline, coal for fires, etc. So even at that, for the US, I guess it would last 2 years if you use it at that rate. So it's a big resource, but actually it's not a huge resource in terms of just our thirst or hunger for natural gas. This is a figure that comes out of Science, the Science magazine, the top, one of the top science journals that itemizes these things. You drill these wells down to about 9,000 feet, 10,000 feet, 3 kilometers. You massively frack it. You have these overlying beds that are the protection between whatever you've done here, liberating these gases, which will preferentially come up the well bore for us to use at the surface. But also, if you haven't sealed in this pipe all the way up through here, you can also get natural gas, fugitive gases coming up through here, both contaminating groundwater, if that happens, and also other leakages from the fracking process that might occur if you get fracking fluids into these aquifers. Typically, these are separated by a long distance. Typically, this might be 500 meters or so, and typically this is the order of 3 kilometers. So 3,000. So there's a big difference. So there's a big leeway. And probably this isn't a big issue, but actually it's a tough thing to be able to prove. And it's a big industrialization problem. This is a frac job. Each one of these trucks is a compressor. Each one of these pipes going out of the truck goes into a manifold, and it ends up in going into a single well. And the reason that they're using all of these in parallel, is it's just providing the volume to be able to jack the pressure up enough to be able to frack the reservoir. And so it's a big industrialized thing in the rural activity. One of the issues, I don't think it's an issue, but people talk about it, is induced seismicity. Again, the fact that when you frack along this lateral, so you drill a hole down, you deviate it at the bottom so it spends a lot of time in the reservoir, you isolate a zone and you pump it up, and you drive a fracture, which you can see here. All these little dots are actually the little earthquakes that result from that. Then you isolate this and you pump up this region here, and you develop a fracture which moves out from the well bore and creates all of this cloud as you basically break open the rock in small fractures. They're very small earthquakes. This is the magnitude of the earthquake, so it's a log scale. Minus 1.4, you wouldn't feel. The earthquake we had here, you were on campus, right? 3 years ago, October 2.5 years ago, right? Was what? Magnitude 6. And so each magnitude is an order of magnitude more energy. So 5 would be 10 times less, 4 would be 10 times less, 3 would be 10 times less. So as you go down here, this is really small. You wouldn't feel it. I'm not sure whether it's the size of, at some stage you're talking about breaking a pencil then, in terms of the size of these things. And so as a matter of generating seismicity in this, there's some seismicity that happens as you frack it, but as soon as you stop fracking, it all goes away. The big questions over induced seismicity, which has happened more recently, there was an event in Youngstown, Ohio, just on the Pennsylvania border. There was one in Oklahoma. There were events in Arkansas and also in Colorado recently. And typically they're not related to gas shales, but they're typically related to taking the water, this 5 million gallons that you use in the gas shale fracking, and then injecting it much deeper into a saline reservoir just to get rid of it. And as you pump those large volumes into these reservoirs, if you pump them fast enough, you don't want to frack it, but you do basically frack it. And if you release pent-up stresses, then this is just the one in the Ozarks. This is Arkansas, where you actually generate earthquakes, which are actually much larger than the ones we looked at on the previous one, which are very close, within an order of magnitude, of the ones that we felt from this event down in Mineral Springs, Virginia, 2.5 years ago. We do get to go to quarter two, right? You're just checking the time, right, on the phone? So, yeah, it is quarter two. So, anyway, so we've talked about most of these things. So these are these big issues. So groundwater issues in the Marcellus is a big issue. Most of the water that goes in is water. Proppant goes in to be able to hold open the fractures once you've made it, but some very small percentage of this are really things that you probably don't want to put in your coffee. They probably stay where they are. I'm not suggesting that there's necessarily a huge hazard, but there is an issue, a move now to disclose, first of all, what these components are as they go into the ground on behalf of the companies, and also to do a reasonable job of monitoring after the fact to make sure that the expectation that they don't turn up somewhere else is really the reality. And the reason that I say there's possibly not much of an issue in terms of groundwater contamination from making a linkage from 3 kilometers to the shallow aquifers, because if you look at just the geometry of these things for the Marcellus, typically the Marcellus is probably 6,000 feet deep, and the potable water would be surprising if it went below. I know the well that I have in my house is 300 feet deep, and so it'd be surprising if it went more than a few hundred meters deep. And so the separation between the reservoir and potable water is a lot. It's a lot in the Marcellus, it's a lot in other shales around the country. The Barnett is the other well-known one down in Texas, Barnett and Woodford in the southwest. And I guess there's also do you remember the name of it? Up in North Dakota? Doesn't matter. Not going to worry about it. So the big energy resource. But there are some data to support some things that are going on that are a little strange, but they relate directly to groundwater. And so this is a report from the Proceedings of the National Academy of Sciences. and it's for some water well data which were taken in the northeastern part of Pennsylvania, right? This is well, you know exactly where this is right from that map. No fracking, of course, in New York. Moratorium on fracking. They won't allow you to inject more than, I'm guessing, 10,000 gallons of water. So if you can only inject 10,000 gallons, you can't frack. So de facto, by limiting the amount of fluid that you can inject, they've not allowed gas production from shales in New York State. But if you look across the border, this is a study looking at the components that are found in people's drinking wells and their relative distance to the closest Marcellus well, which of course will be much deeper. And the data for these are shown here. So the horizontal axis is the distance to the nearest well. So this is right next door to so this is a groundwater well which is right next door to the Marcellus well. This is a groundwater well which is 5,500 meters, 5.5 kilometers away. And these are the concentrations of methane relative to the EPA standard. So this is the maximum EPA standard. If you get in here, you're in a problem. If you get above here, you're in a real problem. And of course, these magnitudes of concentrations in groundwater are high, and they're high as you get closer to the fracking regions. The laterals for these fracking regions are probably 1 kilometer long. And so the fact that you could argue that this material here is coming from the fracking region is probably more likely that it's coming from just not very well sealed in well bores as they come up to the surface. So in other words, doing a bad job on this part here, and so that stuff that comes up to the surface comes around the cement that's here and gets into the groundwater that way. It's probably Marcellus gas, because if you look at the signature, the delta carbon-13 signature, it's thermogenic in origin rather than microbial. Microbial means the stuff that comes from septic tanks, which you obviously don't want to have in your drinking water either, but perhaps you might feel, I'm not sure whether you feel better or worse from it, but the reality is that this is probably the origins of this are probably thermogenic, and they're probably deep methane rather than shallow methane from these other things. And I won't talk about that. So there's a variety of, so we'll talk about this subject relatively broadly. We won't talk about all of these things, but everything we talk about is really fluid flow and fluid displacement in porous media and fractured media. And so basically it addresses these other issues as well.